Great.
Great.
All right. Well, good afternoon, everyone. Thank you for attending today's webinar on the IRC. This webinar is being recorded, and the recording will be posted on the CO Code Adoption Toolkit. If there's any issues with the audio, please write me in the chat. My name, again, is Kira Winkle. I'm a sustainability consultant with NORESCO, and this series is sponsored by the Colorado Energy Office with training materials created by Anna McCullough. Too many slides. There we go. We've been working with the Colorado Energy Office to provide trainings just like this one. This is the first of this webinar series, so make sure to register for the other trainings that are offered. There will be a link set out in the follow-up email if you would like to register for another webinar. And we are also offering tailored group trainings or technical assistance for jurisdictions that are updating I-codes. Please reach out to my colleague, Erica DeLello, to set something up. Let's see. What's this? There we go. Most of you know about the Code Adoption Toolkit and all of the resources available, including the recordings from previous trainings. Today, I want to highlight the code helpline, and this helpline is available to anyone in Colorado on any of the I-codes or REACH codes. So, for example, if you are a jurisdiction and need assistance on a plan review, or a homeowner or engineer with a question about code applicability, you can submit a ticket and a subject matter expert will get back to you within a couple of days. You can access this helpline through the Code Adoption Toolkit through this link. Ooh. Here we go. So throughout the webinar, we do want to encourage questions. So please use the Q&A function, and I will let our presenter know at the end of the presentation. There's also the ability to raise your hand and ask a question at the end of the presentation, and I can unmute you. Lastly, there will be a survey window that pops up following the webinar. So please take a moment to provide feedback so we can continue to improve on these webinars. Today's presenter is Anna McCullough, who is a professional engineer with over 12 years of experience in HVAC design and building energy performance. Before coming to Group 14, Anna designed commercial and multifamily HVAC systems for 6 years. She is an expert in building analysis and using OpenStudio and Energy Plus. And with that, I will hand it over to Anna.
Hi, everyone. My name is Anna McCullough. Kira said, I would love to hear some questions from you all. This is a very high level commercial building science 101 training today. So if you have any questions or you need any additional information, I've left plenty of time for questions. So if anything comes up, please feel free to raise your hand, enter it into the chat, and we will answer your questions at the end. Okay, so as we go through this commercial building science webinar today, we're going to be talking about what is building science. We're going to then discuss the parts of the wall, and then we're going to talk about the perfect wall. I guess I should put perfect in air quotes. I do want to kind of preface this entire webinar by saying this is the kind of ideal solution and kind of easy button. It does not cover all of the complex situations that different buildings will come up against, and the different complex scenarios that we see in everyday designs. So this is just kind of a general recommendation, items that we have come across in our experience through different commercial buildings. And so we'll be talking through, what is building science? We'll talk through why it's important, and then we'll talk through how the wall and the envelope of your building really impacts the building as a whole. So why does building science matter? Building science is really the discussion of all of the different external and internal forces that that will impact the energy use and the performance of the building. So we look at things, in this diagram of a home. We can look through all the different forces that will impact this home, and that's really the discussion of building science. How do all of these forces work against each other and with each other, and how does that impact the performance of the building? When we talk about performance, we're not just talking about energy performance, although that is an important factor. We're talking about the performance of the wall assembly. Can the wall assembly dry when it gets wet? Does it get too hot? Does it get too cold? Is there a potential for condensation? All of those items are what really impact or what really encompass building science. It's a really broad topic. So today we're really going to be talking about walls, because I think that is what we get asked the most questions about. But if you have additional questions, I'm happy to talk about whatever you'd like. So when we look at this diagram, we see kind of the large forces that are acting on the building. We have wind-driven rain. We have radiant heat from the sun. We have night sky radiation when it gets cold in the evenings. We have air exfiltration. So air, if your building's positively pressurized, you're going to have air leaving the building. We have infiltration for when you have those negatively pressurized spaces and you have air coming into the building. Solar heat gain through your glass. We have duct leakage, stack effect, which is we'll talk a little bit more about that, but the impact basically that height has on the external forces, external pressure forces and internal pressure forces on the building. And we have conduction through the ground as well. Last, but certainly not least, we also have vapor diffusion. So we'll be talking about the vapor within the wall. How do we let the wall dry? What happens when vapor gets into our wall? Because it will. And we're going to talk through all of those items today. Again, as you have questions, because I'm sure there will be some, feel free to type them in. So what really is going to impact the science of your building and the performance of your building are your walls. Glazing is obviously a very important part of your building performance, your roof, your slab, your HVAC performance, all of that all work together. But what we're going to be talking about today is your walls. And when we talk about walls, we have 4 control layers. We have a rain control layer, an air control layer, a vapor control layer, and a thermal control layer. And we're going to talk about each of these layers and what they actually mean. What is an air barrier? What is a rain control layer? But what we really want to focus on whenever we're looking at a building is thinking about protecting the structure. Your typical commercial building is going to be a steel stud or a mass wall. And when we think particularly about steel studs, we want to create a wall assembly that will protect those steel studs. They're going to be there for a very long time. We want to protect our structure and make sure that it can also withstand the test of time. So what is a rain control layer? We know that our buildings will experience rain. I cannot think of a location where it never ever rains, although I am sure there are some on the planet. We will experience rain, and particularly wind-driven rain. So not rain that is falling just down nicely, coming off your roof through your gutters and doesn't really drive against the wall. What we're worried about is that rain that comes up hard against your wall and how that is going to impact your structure. So typically, and this is kind of the most common rain control layer we see, we have a cladding system. So we have brick veneer or metal panels that can allow rain through them, and then they hit our rain control level or rain control layer, that rain washes down and comes out the bottom of the wall with a flashing, with a drip edge. This is the most common type of rain control layer, but really there are three types we're going to talk about. The first is storage or mass walls. Then we have barriers and a drained layer. So this is a good example of a drained layer, but we'll go through more here in a minute. Storage or mass walls are also considered to be a rain control layer. So what happens when we have a masonry wall, for example, is that the wind-driven rain hits the wall, and that wall is actually designed to absorb that water and then dry out. And that's the key here, is that when we have these really thick mass walls, they have the potential to dry. And I'm going to talk a lot throughout this entire hour about making sure that our walls can dry out, because it is so important. The next type of rain control layer would be a barrier. So these are portions of your wall that will not, by the type of material they are built out of, will not allow any rain to pass through. So structural glazing, unless you're at a seam, and all of these could have like a little star next to them and say like, unless you're at a seam. But unless you're at the edge of a panel of glass, you're not going to see any potential for rain passing through that glass. Same with steel-clad panels or a face-sealed EIFS. It's an impermeable surface that will not allow for any water absorption. And then the last and most common type of rain control layer is a drained assembly. So rain passes through our cladding system and is controlled via a drainage layer. We have an air gap that allows for the water to drain down the facade of the building and then pass out through flashing. So that's our rain control layer, kind of the most easily understood layer of a wall, in my opinion, right? We want to keep rain out, and we want to make sure that we have a way for that rain to escape if it does get in. The next layer we're going to talk about is an air control layer. This is really important because infiltration can make up 10 to 30% of a building's annual energy use unless your air barrier or your air control layer is continuous. So we're going to talk through kind of this scenario with having a negatively pressurized plenum and how that can impact your infiltration and why an air barrier is so important as we get through these next few slides. So an air barrier is the material that separates the outside from the inside and nothing can pass through it. It is impenetrable. You're not going to get any air passing through it from the outside to the inside. And, you know, the energy codes, as they have developed, have made it even more clear and really emphasized the necessary requirements and performance of the air barrier, making sure that it is continuous. You know, we're talking a lot today about walls because it's kind of the basis for building science, in my opinion. But anytime you have a section where a wall is interrupted by a window, or where your wall meets your roof, or where your wall meets your slab, you're going to have a more complex issue than what we're going to cover today. But the key thing about building science, and if you take away anything from this presentation today, it's that all of these control layers should be designed to protect the structure and they should be continuous. So your air barrier should be continuous. Your thermal envelope should be continuous. We don't want to see those breaks to allow infiltration into the building and drive up your heating and cooling loads. So the requirements for an air control layer is that it is impermeable and it is continuous. And there's multiple examples of that. We're going to talk through exterior air barriers and interior air barriers and what we recommend. But the most common examples we see of air barriers are exterior self-adhered membrane sheets, precast or tilt-up concrete panels count as an air barrier, or interior gypsum board can also be an air barrier. So I put hearts here. I figured I was on theme for February. We love an exterior air barrier. Nobody likes an interior air barrier when you're in a cold climate. So an exterior air barrier, say that 10 times fast, is always recommended in cold climates. We want to make sure that we are not allowing that cold air to get past our control layers and into our structure, because then you're going to run the risk of condensation. And we'll talk through why in a few more slides. But that air barrier, we want an exterior air barrier. It also has the secondary benefit of reducing wind washing within the structure. So you're not going to allow, you have a wind force driving against your structure. With an exterior air barrier, you're going to reduce the impact, reduce that wind kind of blowing through your structure. Interior air barriers are harder to install than exterior. Joints at walls and floors must be sealed. And the benefit of an interior air barrier is that it reduces the moisture-laden interior air from infiltrating into your structure cavity, which is a good thing. But we're going to talk about balancing that risk with your other control layers to still to make sure that we are optimizing the building envelope for your climate and for our climate. Okay, so let's talk through this example. This is an example of an interior air barrier. This is a example of a multifamily building. The spaces, interior spaces, are positively pressurized, which we always recommend, right? We want to have a positive pressure as compared to the outside. We want to have more. The reason for wanting to have a positive a positive pressure as compared to the exterior is that we want to reduce that infiltration. So in this example, we have kind of those fan coil units above the ceiling, and we're creating a negatively pressurized plenum. That fan coil unit, if we had an interior air barrier, would create a negatively pressurized plenum. And because of that, the interstitial spaces between the units, or in a hotel room between the guest rooms, now become negative. So the walls between these units are negative, and they are going to suck air in because we do not have a continuous exterior air barrier. Exterior air barriers are really crucial for reducing the amount of infiltration into a building. We could say that our building has an average positive pressure, so we're reducing infiltration that way, but that is not going to be enough to reduce the impact that wind will have on the pressure of the building. And in a minute, on the next slide, stack effect. So we have two examples here of stack effect, when it's cold outside and when it's hot outside. Across the center of these buildings, we have what's called a neutral pressure plane. And that's where the pressure of the stack effect pressure basically changes. The best way to think about stack effect is to think about it from the idea, we all know that hot air rises. So when it's cold outside, we have these, and this is really, we can talk about it in terms of stack effect on a residential home that's 2 stories, but where it starts to really impact things when we're looking at a multi-story tower, right? So this is a good example. We have our elevator shaft running up the middle. And what's going to happen is when it's cold outside, that hot air rises and exfiltrates from the top floors. And because of that, that pressure is going to try and balance, and we're going to be pulling air in at the ground floors. And that's kind of the easiest way to think about it. And the opposite happens when it's hot outside. We have that cold air exfiltrating to the exterior in the summer, and then that hot air coming in on the upper floors. So stack effect is directly impacted by the height of the building, but really we can reduce this infiltration and exfiltration by providing a really solid, continuous exterior air barrier and not allowing our the air that we have worked so hard to heat and cool and spent so much energy heating and cooling, not allowing that air to escape or have additional loads brought in via infiltration. Okay. The next layer we're going to talk about is a vapor control layer. And oftentimes we hear these being called vapor barriers, and that's really not what we want. So previously, we talked about how important it is to allow a wall system to dry. And we talked about our air barrier being continuous on the exterior. If we have an impermeable vapor barrier on the interior side of our wall, for example, now we can have vapor drying to the exterior from the exterior side of our air barrier, but any vapor that is within your stud cavity doesn't have anywhere to go. It can't cross across the air barrier, and it can't cross across the vapor barrier that you've installed. So really what we're looking for is called a vapor retarder. We want to reduce the amount of water that will infiltrate into the wall system from the interior, right? You think about a multifamily unit, for example, somebody sitting in their living room and they knock over a cup of water and that water hits the wall, and we don't want that water to enter into the wall. But we also want to allow any water that is within the wall to dry. And when I was first learning about vapor retarders, in lieu of a vapor barrier, I was like, well, your wall is dry to begin with. So what do you mean we have to allow it to dry from the inside? And then I had someone much smarter than me talk to me about how wet construction is. So when you are building a building, that building's going to get rained on. When you are installing gyp, you use mud. That mud is wet. When you are putting up concrete, that concrete is wet. CMU blocks, everything is wet. And it takes time for that to dry. That doesn't happen over a week. That happens over months, and potentially even years. And so we want to make sure that those materials that were used to build the building can dry. If we have our exterior air barrier, I should have done like the tongue twister prep for this. Exterior air barrier on the exterior of our building, of our structure, we want to make sure that all of the materials on the exterior side of the air barrier can dry to the outside, and all of the materials on the interior side of the air barrier can dry to the inside. So really important. And then lastly, the last layer we're going to talk about is the thermal control layer. So buildingscience.com has kind of coined the term the perfect wall, and I think we've all heard of it. It is all of your, what we talked about on the first or third slide of this presentation, all of your control layers are protecting your structure. And here is another good example of why that is important. We talked about why it's important to obviously have your rain control layer on the exterior. We've talked about why an exterior air barrier is so important and why a vapor retarder is also important. But what we want to talk about as well is the thermal control layer. We know that insulation is key to reducing the heating loads that the building experiences. It allows us to keep in nice, cool air, and it allows us to keep out cold air. And what's really important in a cold climate is to consider how that insulation is provided. We have two good examples here. The first is of continuous insulation on the exterior without any batt. And then we have the example of batt insulation with no exterior continuous insulation, which I know is kind of an extreme example, but we're using it to illustrate a point. So here with the continuous only insulation, we are seeing that at the inside of R10, it's about 10 degrees outside, maybe a little bit less. We are seeing a 60-degree temperature on the inside face of that continuous exterior insulation. On the example with just batt in the studs, we see a slight 3-4 degree temperature increase at the inside face of the stud. And obviously, you know, at the very inside face of your studs, we're seeing that warmer temperature. But we know that our air barrier is continuous here. And so air is going to be passing through our gyp. It's not sealed. We have nail holes in it. We have punctures from receptacles, light switches, windows. All of that is going to allow interior, warm, moisture-laden air to pass through and into our stud cavity. Your warm, moisture-laden air in the stud cavity is going to see this 15-degree metal and just condense. That water is going to be drawn right out of that warm air in your stud cavity and is going to turn into little droplets. Those little droplets are going to stay there until they can dry out, which may not be too long, but you now are running the risk of having water within your stud cavity that could potentially turn to mold or you know, I can't think of anything much worse, but I'm sure there are worse things. And so this is really, really crucial for steel studs. When we talk about wood studs, a wood stud is much less of a thermal bridge than a steel stud. So, you know, the idea of continuous exterior insulation becomes less impactful in terms of a dew point analysis like this. But when we are looking at a commercial building built out of steel studs, I am always recommending continuous insulation and investing in the correct installment of your continuous insulation rather than providing continuous and batt insulation and potentially using a less effective installation of your continuous insulation. So, we have a question. Kenny, do you want to ask now, or do you want to wait until the end? So you can always ask now. Here, can we unmute Kenny so he can ask his question before we get too far?
Yeah, let me just see how to do that real quick.
Sorry.
That's okay. There we go.
Okay. Yeah, if that R19 was a closed cell or an open cell, is there a potential difference in that dew point or in moisture condensation?
So the location where we're really worried about the moisture condensation is going to be on the outermost face or surface of the steel studs. Because your insulation is kind of packed within the stud cavities, what we're not seeing is any protection for this metal face of the steel stud out here. And that's where we're most concerned about the potential for condensation. Whether or not you have a closed cell spray foam, your steel studs are going to provide such a large thermal bridge that the impact for condensation is still going to be there.
Does the closed cell spray foam help to prohibit or mitigate any of the warm air or the transfer of air through a wall to the steel stud?
So if you had a closed cell spray foam that completely covered your studs, so we're talking about on the inside face, then we would see that reduction in potential for interior air to pass through. But that closed cell spray isn't going to create a fully enclosed barrier around your steel stud, if that makes sense.
It does.
Great. Thank you for asking a question.
Thank you.
So when we are looking at how to most effectively install this continuous insulation, we want to avoid what are called Z-grits. We have all seen them. They are the most common way to, we see them all the time. They're built on almost every building. And really, these Z-grits have the potential to reduce the effective R value of your continuous insulation by 20 to 40%. So if you are installing an R10 continuous insulation and you install just plain old metal vertical Z-grits that are running in parallel with your steel studs, you are going to see a potentially up to a 60% reduction in the effective R value of that continuous insulation, which is a really big deal. And this is why, I really try to emphasize the importance of making sure that the materials and the particularly the insulation materials that we're using are being used correctly. If we install R10 continuous insulation with no batt, and we have vertical Z-grits that are continuous with our steel studs, it's like installing a potentially as low as an R4 on the exterior of your wall. And so what we really want to do is take that money, easier said than done always, but take that money that we were going to use to pay for our batt and our batt installation and use it to install a more insulative, more effective exterior insulation. So no continuous Z-grits. There are multiple ways to do this. We see the fiberglass clips. We see horizontal Z-grits. We see you can use vertical and horizontal. But in my experience, the most palatable way to do this is to use hat channels and long screws. So you have a hat channel on the exterior face of your continuous insulation that is held to your structure via a long screw. This is still a thermal bridge. We're still going to see a reduction in the effectiveness of our R value, but rather than a 40 to 60% reduction, we're going to see a 5% reduction, depending on how often you have the screws, but it makes a significant impact to not use Z-girts. Those fiberglass clips are great. They are another great option. They will, reduce your the effective R value of your insulation by 15% or so, but we do see, it really depends on the application and how this is being installed. So again, I'm making these recommendations as considerations. They are not going to be the end all be all, laser shot, perfect solution for every building, but this is what we recommend as a starting point. Okay, so we've talked through our 4 layers. We've talked through the thermal control layer, vapor control, air control, and then rain control. And now we want to put all of those together and talk about what the perfect wall is. So this is a wall that is allowed to dry from the exterior side of our air barrier out, the interior side of our air barrier out. All of our control layers are protecting our structure that we so want to protect because it is so expensive. And we are using this wall and we'll just talk through the different parts of it very quickly. So we have our veneer or a cladding system, a drained cavity that allows for rain control. We then have our exterior rigid insulation. This could be most often lately we're starting to see mineral wool because people are starting to think a little bit more about the embodied carbon of the different insulation types of insulation that they use, but we'll see a polyiso, an XPS, or a mineral wool. And then we have our membrane, air barrier, and vapor retarder located on the inside surface of our exterior insulation. Then we have our JIP, our sheathing, our uninsulated steel cavity, the JIP board, and then any sort of semi-permeable wall finish that allows for any vapor that is within the steel stud cavity to dry. The key here is, and I think something that we always hear from, we have a division of our company that is solely dedicated to building enclosure. And what they always gripe, their biggest gripe is when people talk about where their vapor barrier should be. And it's not, we always want to talk about a vapor retarder. And make sure that we have the language around the control layers of our walls. We want that language to be correct so that we are all talking the same language and making sure that we understand the goal of our wall is to protect our structure and protect our building. The next kind of perfect wall that we're going to talk through is a mass wall. So again, very, very similar. We have our veneer, a drained cavity that allows that rain to exit our cavity, the exterior rigid insulation, a vapor barrier, a class 1 vapor retarder, or as well as our air barrier. Then we have the concrete block. This can also be precast. Metal channel or wood furring, JIP board, and then the semi-permeable textured it doesn't have to be textured, but wall finish, right? We want to have a wall finish that again will allow this concrete block to dry from the construction and from any sort of condensation that happens within that concrete wall block. We want to allow for it to dry to the interior. And then we want to allow for any sort of water that gets in through our drained cavity. We want it to dry to the exterior as well. And that was what I had for you. I wanted to leave a bunch of time for questions. Here is the slide on the Colorado Codes helpline. And please, if anyone has any questions, feel free to ask them. If you do not, if you think of them later or don't want to ask them now, you can always reach out and I'm happy to answer any questions you have. One question, will we have access to the recording of this webinar? Yes. I believe so. Well, Kira, correct me if I'm wrong.
Yes, the recording will be posted to the Colorado Energy Office Toolkit website. I'll put a link to that in the chat. I do think it might be a couple of weeks before we get it posted, just to let you know.
We had a good question. Is the air vapor barrier the same layer or I am so sick of saying ours today, or are they always separate layers? So an air barrier by definition will not allow vapor through it, right? They are inherently will not allow any sort of air that is holding moisture. You can't pass any air through the air barrier. So any air that has moisture within it will not pass through. And so it is a vapor barrier. But when we talk about the vapor barrier, we also want to talk about the other locations within the wall where we typically previously have seen that a vapor barrier needs to be called out separately. We want to make sure that we're talking about a vapor retarder. Can we avoid continuous insulation by modeling alternative strategies? That is a great question. So you can, you know, as an energy modeler, I very often get this question that continuous insulation is very expensive. It doesn't pay back. Can we just put that in and install really effective lighting, really efficient lighting, and save a bunch of energy and still pass the code? And you can do that. We can absolutely, well, the majority of buildings we can get you through without providing continuous insulation. It is not recommended though. The energy model does not take into account things like condensation within the wall assembly, potential for mold growth, and all of those items that we really need to consider for creating a wall that is going to, and a structure that's going to withstand the test of time. If you're talking about a wood structure, like I said, this becomes far less important. Well, continuous insulation becomes far less important. We're really worried about steel studs. And then also, you know, we want to optimize the mass wall as well to make sure that we aren't allowing for the creation of, or well, allowing for too much thermal energy passing through the mass wall. Another question, it sounds like an air barrier will prevent vapors from passing through. If that is true, what role is the vapor retarder really providing if drying to the outside? It does, it trips me up as well. And so the idea is, right, we're going to allow the wall to dry, but we still want to reduce the amount of water that can get into the wall. If we have a vapor retarder on the inside face of the wall and a vapor retarder within our assembly, what we're going to see is that, you know, the wall is going to get wet. And we want to reduce the amount of water that we are allowing to pass through that inside face of the wall and get into your cavity, because we all know more water, any water in a cavity is bad. But we still need to allow for it to dry. So it's kind of a double-edged sword in finding that balance between making sure that we don't allow water into the wall assembly, but also allowing for it to dry out. It's a very complicated situation, and one that we could probably talk about for a very long time, trying to make sure that we have all the correct language around the optimal way to build a wall and reduce the potential for mold growth. Thank you for all the questions. And let me know if I didn't answer any, or if you have any additional follow-up questions. Yeah, happy to answer any questions you have. I find the priority order to be water, air, thermal, vapor. Agree. As if one misses the air control, then the thermal and vapor will struggle to perform. If one gets water, air, and thermal right, vapor will be much easier if it doesn't take care of itself. That's a great way to think about it, right? And just to repeat that more slowly, because I don't know if you all can see the questions or the question and answer box, but the priority, I find the priority order to be water, air, thermal, vapor, right? We don't want the water, we don't want the rain to come into the building. We don't want the air to come into the building. Then we want to keep the building warm, and then vapor is kind of our lowest priority in that list. If one misses the air control, then the thermal and vapor will struggle to perform. Absolutely true. If one gets water, air, and thermal right, vapor will be much easier if it doesn't take care of itself. It's absolutely true. That's a great way to summarize it. There's a comment, Eagle County is having Joe, I can never say his last name. Somebody's going to have to say it for me, but lecture tomorrow from building science, and he is just, he's awesome. So he's going to put me to shame. Absolutely. He is colorful too. Yeah, I've been to a couple of his lectures, and he is just so, he gives such great presentations. If you guys can get him to come in and teach you about building science, I mean, can't recommend him enough. All right. Well, if there aren't any more questions, that was all I had for you today. I'll put the Colorado Codes helpline back up there. There you go.
All right, awesome. Thank you very much, Anna, and thank you everyone for taking your time today to attend.
Have a great day, everyone.
Bye-bye.
Bye.